Hello everyone and welcome back to Techmine Guru. I'm your coach Supratim. Today we are diving into data structure algorithm lecture 27. Previously we discussed binary search on arrays where we were primarily searching for an index. Today we are going to experience a paradigm shift. We are going to master the art of guessing the perfect minimum or maximum. This is known as binary search on answers, where we are searching for a capacity or trying to answer questions like what is the minimum time needed. So here is the today's journey. Today we will tackle the painter's problem followed by its search space. Then we will observe some master pattern, and finally we will see a problem known as aggressive cows. So let's start with question 1, that is the painter partition problem. So imagine we have an n contiguous boards with varying lengths, and we are given that one painter takes 1 unit of time for 1 unit of length, and we have in total k number of painters available for the job. Our goal is to find the minimum time required to paint all boards. So these are all boards length which are given as an array element. So let's look an example with the sequence of boards 3, 5, 1, 7, 8, 2, 5, 3, 10, 1, 4, 7, 5, 4, and 6. And suppose in our question, the k is given as 4. So consider the what if scenario. So for the left boundary, what if we had 15 painters, meaning one painter for every board? The time taken is simply the length of the largest single board, right? Because till the time this painter would paint this, all of this will get completed by the individual painter. So what is the maximum amount of time needed for a single board to get painted? It will be 10. And suppose what if we had only one painter? Then sum of all the elements will be the time taken by that painter to paint all the boards. So what is the sum of all boards? Is 71. So our search space will lie from max of a of I to sum of a of I. That is maximum time taken for a single board to get painted will be taken as L, which is 10. And what is the total time that can be taken to paint all the boards if only one painter is there? That is sum of a of I will be taken as the right pointer. So our search space will be from 10 to 71 only. So our binary search will be running from L is equal to 10 to R is equal to 70. So if you have closely observed, instead of searching the whole array, we are now searching over the answer. So let's take a midpoint of which is L plus R by 2. So 10 plus 71 by 2 will give the result as 40. So we then ask, can k painters given in the question finish the entire job if we give them a strict time limit of 40? Our core algorithm uses a while loop where L is lesser than equal to R. We calculate mid and then call a function P, which will be equal to min painters passing the array and the mid. This acts our validation engine to ask, can we do it? It sets a strict deadline of mid time. Engine checks the array sequentially and return the number of painters needed. Suppose if the total painters needed is less than or equal to k, so then it's possible. So we then ask, can we do it faster? Means can we need some less timing? So for that, we will squeeze our time by making R is equal to mid minus 1. But what if we need number of painters which are greater than k? Then it is impossible, right? Because we have been already given that you can take at most k painters. So now it will be impossible, and so we need more time. So for that, we need to go to right. And for going to right, what we do? We do L is equal to mid plus 1. So if count of painters is lesser than equal to the number of painters given, which is k, then in that case, we just need to see whether we can squeeze the time or not by going towards the left. And for going towards the left, we will do R is equal to mid minus 1. And if count of painters needed comes greater than the given k, then it is impossible and we need definitely more time. For that, we will go right and we will do L is equal to mid plus 1. So this mid equal to 40 will be like asking a question that can k painters finish the entire job if we give them a strict time limit of 40. So let's see the core algorithm. So the core algorithm says that our search space is between the maximum time needed to paint the longest board, which is L is equal to max of a of I, and R will be the total time which can be needed if there is one painter. That will be given as sum is equal to a of I, and that we will consider as R. So our search space is from max of a of I to sum of a of I. So we ran a loop from L to R. So we calculate the mid using our formula L plus R minus L by 2. And here we will call a helper function min painters, which will take array as an input and the time. And if min painters needed is lesser than equal to k, we will simply update the answer by taking the min of the answer and the mid element and by moving towards the left side. And what we do when we want to move towards the left side, we will do R is equal to mid minus 1. Mid will tell the minimum time which is needed. And when P is greater than K, that time we will move towards the right. And for moving towards the right, we do L is equal to mid plus 1. So let's see them in each round. Suppose round 1 gives us mid as 40, right? So if we have 40, so how many painters we need? So if you keep on counting till here, so it will be 34. And after that, this 10 will make it 44. But we have 40 amount of time for each painter. So this painter will paint from here to here. So that will be like 34 units of time this painter will take. So if you see, from 10 to 7, there will be 22 units of time needed for the second painter. And similarly, for the third painter, it will need 15 units of time. So how many painters are needed in this? 3, right? Since we have been given in the question that k is equal to 4. So we can still check, since total painters needed from this is 3, which is lesser than the painters given. So we can see that if we can squeeze the time by using the spare painter. So in the round 2, we will squeeze it. So for squeezing the time, we will make r is equal to mid minus 1. Now our r will be 39, since our previous mid was 40 and L is 10. So now what will be our current mid? 10 plus 39 by 2, which is 24. So if you again start moving in the array, you will see 3 plus 5 plus 1 plus 7 plus 8. So this will be 24 units of time, which is used by the first painter. Now for the second painter, it will be 2 plus 5 plus 3 plus 10 plus 1. It will be 21. If we include this one also, this will be 25. But our maximum time needed for the round 2 is 24 only. So we are going to use 21 units of time for the second painter. So this will be our second painter. Similarly, for the third painter, paint 4 plus 7 plus 5 plus 4. It will be 20, right? And if we include the last one as well, it will be 26 units of time. But the maximum time which can be used in this round is 24 only. So our third painter will paint till this 4. And since we have one more painter left, so that painter will paint this 6 units. And now finally we got the number of painters. We will update our answer and we will move towards the left side so that we can see that if we can squeeze the time further. So what will be the new time now? So what will be the new r? It will be 23 and our L will be 10 only. So what will be our new mid? It will be 23 plus 10 by 2, which will come as 16. So if you see 16, for that we need 5 painters, because this much amount will be painted by time by one first painter, then this 8 plus 2 plus 5. This much will be needed for our second painter. This much will be needed for our third painter, right? Because we cannot use 4, because right now our maximum time which we can take is 16, right? Now this much will be needed for our fourth painter, and this remaining 10 units will be used by our 5 painters. But in the question given, we have only 4 painters. So this will be discarded. That time we will move towards the right. And for moving towards the right, we will do L is equal to mid plus 1. Now our L will become 17, right? Again, when we will do 17 plus 23 by 2, which will give our mid as 20. So if we see with the mid as 20, that time this much time will be taken for the first painter. From here to here, our second painter will take time. And if you see, our third painter will need this much time. And our fourth painter will paint this much only, because 6 cannot be accommodated, because if we include the 6, it will become 22. And our last painter will be this. Again, it will come 5. So again, we will do L is equal to mid plus 1. Now our L will become 21, right? Now we will again take out the mid. 21 plus 23 by 2 will give the result as 22, right? So if we have 22 unit of time, then how much time will be needed? Again, this much will be given to the first painter. From here till here, second painter will take this time. Now, since we have 22 units of time, we can include this one also for the third painter, and our fourth painter will take the remaining 15 units. So again, number of painters needed will be 4 only. Now we will update our answer to 22 and we will move towards the right side so that we can squeeze the time further. Now what will be our R? It will be 22. So again, if we do 21 plus 22 by 2, we will get the result as 21 as mid. So again, if we check for 21 units of time, it will come as 5 painters. So again, we will make L as mid plus 1. So now our L will be 22. And here we will break out from the loop, because in our next iteration, the L will become 23. Since in that iteration also, we will need 5 painters. So if you calculate this, you will get 5 painters needed. So let's see how min painters gives the minimum number of painters needed for a desired time. So suppose in min painters, you take the array and you have been given the time. So we have initialized 2 variables, answer is equal to 1 and painter needing the time as x. So why answer is equal to 1? Because we know that at least one painter is needed to paint all the boards. So we ran a loop from for I is equal to 0 to n minus 1. We checked whether any element in the array is greater than the time given. So if the time given is very less than the time needed by any of the elements, we will simply return -1. And then we will check if the time is greater than a of I. If the time is greater than a of I, we will subtract that element from the painter's time. So suppose if we take this example, so what is x here? X will be 40, right? So our p of time will be 40. Is 40 greater than 3? Yes. So we will make the first painter paint this, and that will decrease the painter's time. So what is the remaining p time needed? 37. Similarly, in the next iteration, 5 will get subtracted. So what is the p time left? 32. Similarly, in the next iteration, 1 will be subtracted from the p time. It will be 31. Now 7 will be subtracted. It will be 24. Now in the next iteration, 8 will get subtracted. It will become 16. Now 2 will get subtracted. It will become 14. And finally 5 and 3, when they will get subtracted, it will become 9 and 6. So till now, our p time became 6. So with this 6, can we paint the 10 unit of board? No, right? So we will come to the else block. So now our answer will hold the 2. Why? Because we need a separate painter for this. Since this is a fresh painter, we will again allocate him the paint time to be 40, and we will subtract the current element from our painter's time. So now our painter time will become 30 for the second painter. Similarly, for this 1, 4 and 7, it will become 29, 25 and 18, right? And similarly, the second painter can paint these 3 as well. So it will become 13, 9 and 3. So for this array, how many min painters will be needed? 2 only, right? But we have been given 3 painters. So we can use one more painter and we can squeeze the time. So suppose when we are squeezing the time, our new timing becomes 24. So now this P time will hold 24 in it. Now again, we will check whether any element is greater than the time given or not. We will return -1 directly from there. So this is like handling a edge case, and we will see if 24 is greater than 3 or not. For painting this one, we will reduce the time for that particular paint. Now the current P time will be 21. Now in the next iteration, again 5 will get deducted. Now the current P time will be 16. In the next iteration, 1 will get deducted. Our current time will be 15. Now in the next iteration, 7 will get deducted. Our current P time will be 8. And finally, in the next iteration, our P time will become 0. Now in the next iteration, we will see our P time present is 0, but our A of I is 2. So this if will not work, we will come to this else block. Our answer will become 2 again, right? Because here we are allocating a new painter. Since we are allocating the new painter, again P time will be made now as 24. Since 24 is the time allocated for any painter in this min painter function. So again, from this 24 time unit, we will deduct 2. It will become 22, right? Again, on the next iteration, we will deduct 5. This will make it 17. Then again, in the next iteration, it will make it 14. Again, in the next iteration, it will make it 4 because 10 units it will take consume here. And again, in the next iteration, it will make 3. Now, our P time will be lesser than the time needed for the next board. So again, we will increase our answer because from here, a new painter will get started. So our answer will hold now 3. Now again, this new painter will get its 24 unit of time. Again, we will deduct 4 from this 24 units. It will make 20, right? Again, on the next iteration, 7 units will be deducted from the remaining time of the current painter. So now it will become 13. Now in the next iteration, again 5 units will be deducted. Our current painter's time will be 8. Again, in the next iteration, 4 units will be deducted. So our current painter time will be 4 units left. And with this 4 units left for the current painter, we cannot paint 6 units of board. So this condition will fail and our code will come to this block. Again, answer will become 4. Now our fourth painter will start. Now again, the time allocated to the fourth painter will be 24. And finally, from his 24, 6 units of time will be taken to paint this board. So our answer return will be 4 now. So since our answer returned is 4, now we will do r is equal to mid minus 1 to check whether we can squeeze the timing or not. Since we have already understood just now that even of squeezing the time further, we are not able to get the answer better than 24. So we will finally update our answer 24 and we will return the same. So what is the minimum time needed for this complete board to get painted by 4 painters? It will be 24. So let's understand the time complexity of this. Since we have seen that this is running one for loop, that is from for I is equal to 0 to n minus 1. So here our time complexity will be O of n. And since we are not taking any extra space, our space complexity will be O of 1. And for this, we need On time complexity to calculate the sum of array, and to calculate the max from the array, we need On again. But for this binary search to run, we need O of log of search space. And what is the search space? Search space is between max of A of I and sum of A of I. So our total time complexity will be O of n into n taken by the min painters function, and this is for binary search, which is log of search space, which is sum of A minus max of A. And since throughout this code we have not taken any extra space, our space complexity will be O of 1. So let's see the next problem of our day today, which is aggressive count. So here we have n stalls located at ascending positions, and there are C aggressive cows given that needs placement. So the goal is to maximize the distance between them to prevent fight. So here we are essentially searching the distance D, and we want to find the maximum cows which we can place if a minimum distance D is strictly maintained. So the distance timeline ranges from 1 unit to A of n minus 1 minus A of 0. That is distance of the first cow to the last cow. So this is our search space here. So let's see the code how we can solve this. So in this again we will use one helper method which will give that how many cows we can place if we are given a certain distance. So again we have taken answer is equal to 1. So since at least one cow will be there, right? And we can place that first cow in the first position of the array. Suppose we have kept the C1 cow in the first position. In this we will run a loop from for I is equal to 1 to n minus 1, and we will check from each element that how much distance it is there. If that distance is greater than equal to the distance given, we will say that this is the minimum distance and cows will not fight. So if the cows will not fight, we will keep one another cow, and for that we will do answer plus plus, and we will update the position of that cow, so that going forward when we do iteration, we can check with respect to that cow. So this max cow will tell us that on the given d distance, how many cows we can keep. So what is our search space here? Search space, as we have already discussed, will be L is equal to 1 and R is equal to A of last element and A of first element. So 43 minus 2, which will be 41. So R will be equal to 41. So what will be our mid? It will be 21 distance. So we will call our max cows helper function. We will keep L is equal to 2 now, right? And our D here is 21, right? We will check the next element, which is, we will start a loop from I is equal to 1 to n minus 1. So 6 minus 2 is not greater than 21, right? So our answer will not increase. So we cannot place this C2 cow here. Now we will move towards the next element, which is at 11 position. Again, we will do 11 minus 2, which will be again not greater than 21. Again, we cannot place the second cow here. Now we will again move to the third index, which is 14. Now we will see 14 minus 2, which is again not greater than 21. So again, we cannot place it here. Now we will move to the next index, which is 19. Again, we will do 19 minus 2, which is again not greater than 21. Again, we will move to the next index, which is 25. This time, 25 minus 2 will be greater than 21. So here we can place our second cow, and we will update our second cow's position. Now L will be updated to 25. Now we will again check the next element, which is 30. 30 minus 25 will not be greater than 21, right? So we cannot place the third cow again. Now we will move to 39. 39 minus 25 will be again not greater than 21. We cannot place the third cow here. Now we will again move to the last element, which is 43. Since 43 minus 25 is again not greater than 21, so we can place only 2 cows here. But we have to place 3 cows at least, right? So we have to decrease the distance between them. So for that, we will do R is equal to mid minus 1. So now our L is 1 and R is 20. Why? Because our earlier mid was 21. So what will be our current mid? 10, right? So with 10 as a mid, we can place the first cow C1 at 2 position, and the next cow which we can keep is at 14 position. Why? Because the distance between them will be 12, which is greater than the 10, right? So the second cow position will get updated to 14, and now we will again iterate on the array. So the third cow can be placed at 30th position, because the difference in the distance will be 30 minus 14, which is 16, which is greater than the 10. So we can place our third cow in the 30th position. Similarly, for the last cow, we can place it at 43 position. So now we can keep 4 cows, but we have originally present 3 cows. So to decrease the number of cows, what we will do? So when count of number of cows is greater than the given cow count, that time we will do L is equal to mid plus 1. That time we will try to increase the distance. So now our L will be equal to mid plus 1. What was our previous mid? 10. What will be our new L? Which will be 11. So now our mid will be 11 plus 20 by 2, which will come around 15. So now again we will call this max cows function. Our first cow will be at C1 only, and our second cow will be now at 19 position. Since 19 minus 2 is 17, which is greater than the distance given, right? So our second cow will be at the 19 position, and similarly our third cow will be at 39 position. And now we have exactly C number of cows needed by our code. So what is the max cows needed if we have distance 15, which will be 3 only. So now again we will see whether we can increase the distance little further as well. So for that, we will move towards the right side, and for moving towards the right side, we will do L is equal to mid plus 1. So our previous mid was 15. Now our L will be equal to 16, and R will be same only. Now our mid is 18. So if you see the 18 distance, you will see our first cow when placed at 2. So what is the next cow which we can place so that the difference is 18? So this will be 25, right? So our next cow we can place at 25, because our distances between the 2 cows will be 23, which is greater than 18. And our third cow can be kept at the last position, since the difference is valid. Since again we got C number of cows, we will again update the answer, and we will do L is equal to mid plus 1 to check whether we can increase the distance or not. So now our L will become 18 plus 1, which will be equal to 19. So our mid will be 19 plus 20 by 2, which will be 19 only. So if we keep a distance of 19, we can place first cow here, and the second cow will be here only. And we cannot place the third cow, because if we try to place the third cow, the distance will be 18, but the distance needed is 19. So our number of cows will be 2 only if we keep a distance of 19. Since number of cows is lesser than the given cow count, so we will do R is equal to mid minus 1. So our R will become 18 now. Since R is lesser than L, so we will come out of this for loop, right? So our final answer will be 18. So 18 is the maximum distance in which we can keep 3 cows, which is given, and that is the maximum distance possible. So if you see the time complexity, since this max cows function is running from for I is equal to 1 to n minus 1, so here the time complexity will be O of n, and since we are not taking any extra space inside this max cows function, so our space complexity will be O of 1. And since this is binary search, so our time complexity will be log of search space. So what is our search space? A of n minus 1 minus A of 0. So what is our total time complexity? N taken by max cows function and log of search space taken by binary search algo. And since in both the code we are not taking any extra space, our space complexity will be O of 1 only. So to bring it all together, there are two flavors of binary search on answers. So you are either trying to minimize the maximum, which you did in the painters problem, right, where you searched for capacity or time. So your validation goal is, can we fit in? If valid, you save the answer and squeeze tighter by going left, setting r is equal to mid minus 1. And in the next one, we used maximize the minimum distance possible, like in the cows problem, where you search for distance. Your validation goal was, can we stretch it further? And if it is valid, you save the answer and push further by going towards the right side. And for going towards the right side, you do low is equal to mid plus 1. So how do you spot these problems in the wild? So you look for the master pattern. So the pattern will be first the setup, where you will see 2 or 3 parameters or constants such as array combined with painters or cows, something similar like that. Next, the pattern will be the trigger phrase, where you are explicitly asked to minimize the maximum or to maximize the minimum. And the final thing, which will be the hidden rule. So the problem here will be monotonic in nature. That is, after a certain limit, it will suddenly become impossible or vice versa. So now you know the art of halving the answers and not just the array. So that concludes our deep dive for today. If you found this video helpful, hit that like button and subscribe to Techmine Guru. In the next lecture, we will learn some more interview problems on binary search on arrays and answers. Till we meet again, keep learning, keep coding, and keep optimizing.